Welcome to the third session of 12th module on Big Data Management in Smart Grid Analytics. In previous session, we understood various use cases pertaining to smart grid using big data. In this session, we will focus on the grid analytics logical architecture. We will also look at grid hierarchical model, and then we'll look at some of the examples, including forecasting, scheduling, load analysis. Then we'll look at analytics based on Synchro Phasor, real-life implementations of Synchro Phasors, and the benefits derived from those deployments. We'll also look at analytics based on AMI and examples of benefit derived from those deployments. So let's look at the overall logical architecture. Analytics logical model. It is a logical view of analytics deployed on smart grid. It has three components: synergy model, services stack model, and the component model. We'll look at synergy model in detail. The analytics logical model consists of three views: analytics synergy, analytics services stack, and analytics component. The synergy model illustrates the key concept of smart grid architecture, the manner in which data sources from the grid produce data which, when processed in multiple ways through multiple analytics, can support multiple business outcomes. Therefore, data sources such as various sensors and analytics processing tools and components can and should be shared over multiple capabilities. By arranging the architecture to take advantage of the synergy, the smart grid architect can minimize infrastructure cost while maximizing the realized business benefit. While the synergy model is complex and can be difficult to understand, it has the potential for high payback. In this synergy model diagram, data sources are arrayed at the bottom. Data from these sources falls into one or more of four data classes, as shown in the second tier. In the third tier, 6 classes of analytics process data from the data sources according to data class. In the top tier, analytics support one or more utility business processes. Line color doesn't have any significance. It's used only to illustrate the groupings. Finally, because visualization is pervasive, it is shown as blue box in the synergy model third tier, especially underlying all of the analytics classes, signifying their use in GUI based decision support. And we look at analytics services stack model. This model has foundation component, core component, integration, and support services. In the foundation component, there's a data collection, data aggregation, visualization, reporting, etc. Whereas in the core, it's about data processing, digital signal processing, event processing, grid state processing, etc. And the integration, it's about analytics management, and there are multiple support services needed to provide this services stack. Then the third part of this logical model is analytics component model, which has number of components like DSP engine, data mining tools, visualization tool, event pricing engine, data collection engine, etc. Analytics logical model, this illustrates how different data sources are analyzed in the smart grid, and these analytics feed into multiple business processes. Even though data is coming from multiple different sources, it is combined and analytics is generated, which feeds into multiple business processes. And while doing so, it uses the services from services stack and is realized through components which are illustrated in component model. So this model was built as part of IBM, Cisco, and Southern California Edition smart grid reference architecture. Now let's look at the structural view of smart grid. As we can see, the grid is made up of multiple levels. We have devices which are consumer owned at the bottom layer, and then we have devices which are utility owned. There are multiple networks like premises area network, field area network, local area network, wide area network, and the backbone through which data moves from different sources to the utility data center. Data moves from devices to utility data center. The structural view for analytics also plays big role in illustrating the fact that analytics has to be spread out across the grid. It is not that we deploy analytics model only in data center, but these analytics has to be deployed at multiple different layers such that it can react to events and take corrective actions. For example, if you have a very expensive transformer and when you're collecting the information from transformer, one way is to send all this data back to the data center. But the time it may take to send this data, perform analytics, and take corrective action may be too long. For example, if a truck crashes into transformer, in such event, transformer analytics should be quick to perform the calculation and indicate that it should be isolated from the grid and the area should be reconfigured. That is why the hierarchical model of grid is a very important and easy way to understand how analytics can be deployed at different layers. In this model, we have provided a prescriptive guidance. What are the different analytics, like power quality related analytics, like usage based analytics, like phasor measurement unit related analytics? Where should these models be deployed into the grid? This work is also done as part of the smart grid reference architecture work, which was done in collaboration with Cisco Systems, IBM, and Southern California Edison. Now we look at some of the analytics. The first one we are focusing on is forecasting and scheduling load analytics. Accurate load forecasting is very important for running a reliable system. Similarly, we have to have accurate demand forecasting and match it up with the load forecasting. Usually in summertime, when we have peak loads, that is the time we can also receive very high illumination and generate solar energy. So with smart grid data, the solar energy can easily be integrated into the grid and it can meet the demands of critical peak. Hence, incorporating various renewable sources into grid becomes very profitable for the operator. Load forecasting models must also consider weather and energy trading conditions. So this was about the load forecasting and scheduling analytics. Now let's look at some of the analytics around Synchro Phasor. So it helped quickly identify and rapidly correct system instabilities. For instance, if there are issues in frequency oscillation, as it is sampling at very high rate and it is sending the data for the analytics. So analytics can process that information and provide the corrective actions. Low voltage identification, operating transmission line at greater capacity. With the help of the analytics, we understand the stability of the line, and because of that, we can operate the line at much higher capacity because we understand how stable the line is. It also prevents outages because now we are aware of events and other details happening in the grid. It helps monitor phase, and phase is one of the critical component that must be measured. We'll see some of the examples in the follow-on slides where we see that because of the correct measurement, utilities were able to take corrective actions. It helped operators detect potential failing equipment as well. So with these various analytics, we are able to analyze and take corrective actions. The output from analytics can also feed into engineering, design, and real-time operations to significantly improve the system reliability. And in future, when we have integrated view, so it can be integrated into control system, receives real-time alerts, and even automate system interventions to prevent minor disturbances from cascading into regional outages. And this was like one of the cause of a very large scale outage in US in I think 2003, where almost 30-40% of the population was without power. And that happened because there was no such system to measure the change in the phase and its cascading impact. It started as a small change but resulted in large scale outage in eastern part of the US. Some of the other examples of synchrophasor deployments, like in 2008, 14 transmission lines taken out of service by Hurricane Gustav. With the help of synchrophasor, they were able to form an electrical island, diagnose and mitigate instabilities within that island, and prevented the blackout of New Orleans and Baton Rouge area. Another example, American Transmission Company identified and replaced a potentially failing transformer, avoided an extended transmission substation outage. With this data, lines can be safely re-energized. One of the instances, when a critical 500 kilowatt tie line between Arizona and California tripped in October of 2013, near real-time PMU data allowed system operators at WECC to determine that the line could safely be re-energized almost immediately. Without having this data and analytics, it would have probably taken many days to perform the re-energization. Increased engineering analysis. The ISO New England, which is Independent System Operator of New England, event analysis application now automatically collect and analyze synchrophasor data from PMUs all across New England, enabling engineering to analyze 2 or 3 events per week, up from 2 events per year. So you can see, there is a remarkable difference. Things which you could do only once or twice a year, now you are able to do within a week. We'll look at some of the analytics based on AMI data. We have already discussed some of the analytics related to rates. So in this session, we'll focus on operations and maintenance improvements. AMI data provided the improved billing accuracy, which resulted in lower number of calls back to utilities. Meter data analytics also helped in detecting the health of the meter, and now utilities can proactively replace meter if its analytics determine that that meter may fail in coming days. It also enabled programs like prepay billing. So prepay billing rollouts helped utilities to manage their cash flows. Other scenarios where AMI analytics was deployed is for fault isolation and restoration in the distribution network. Some of the examples of AMI deployments are like faster service restoration. PECO restored services for 37,000 customers, an estimated 3 days faster during a February 2014 storm. It saved over $1.4 million by restoring power 1.5 days earlier. Restored power 2 to 3 days sooner following Superstorm Sandy in 2012. When a fault occurs on a power line or a power line damage, when a fault occurs or there is a power line outage, these smart technologies work in tandem to detect and clear temporary faults, isolate these faults, and automatically reroute power around faults, often within seconds. So this whole reconfiguration of grid is feasible with the help of these technologies. The other fringe benefits are it avoided truck rolls. Almost 6,000 truck rolls were avoided by PECO because now utility is able to get the analytics and the data and make use of it instead of sending their employees to go to different locations and understand the fault, understand whether the asset is working or not. For meter operations between 2011 and 2013, Tri-State Electric Membership Corporation realized 65% decrease in annual meter operations cost. Another example, Central Main Power System, there was system-wide AMI deployment reduced its meter operation cost by more than 80% with annualized saving of about $6.7 million. The other benefits like Tri-State's payback period is less than 5 years for its entire smart metering investment. So what we have seen is there are multiple benefits of smart grid, and the analytics derived out of smart grid can help utilities in multiple scenarios. In this session, we learned about logical model. We have also seen the hierarchical model and various examples where utilities derived significant value from their investment in smart grid. Thank you.